Hi friends, so today we will discuss the detailed account of energy in nuclear fission, that is, why the difference in energies required for the uranium-235 and uranium-238 and the energy distribution of the fission fragments. Okay, so we found that the cross-section for the uranium-235 is very large in thermal region and is decreasing with increasing the energy, whereas for uranium-238 in this region less than this MeV region, there is no cross-section, means no probability for the nuclear fission, and the cross-section is considerable only after the 10⁶ region, means MeV region, which means that the uranium-238 is fissionable only by fast neutrons, but the uranium-235 is fissionable by even the thermal neutrons. And we already had discussed the activation energy. What is meant by the activation energy? The activation energy for the uranium-236 is calculated as 6.2 MeV, and the activation energy for this uranium-239 is calculated as 6.6 MeV. And these activation energies are explicitly depending on the mass number and also on the proton number. You can see this difference as the proton number increases, means heavier and heavier elements, the activation energy becomes larger, and also as the mass number increases, the activation energy is again increasing. So this is the common trend. So, and these are the calculated values for the uranium-236 and uranium-239. But only using this activation energy we cannot explain this fact. Okay, so what is the reason behind this uranium-235 behavior and uranium-238 behavior? So the next type of energy is the excitation energy. So the excitation energy is the energy difference between the excited compound nucleus formed by absorbing the neutron and the ground state of that nucleus. Means this mass difference in the C square. So for uranium-236, the mass of the excited energy of the compound nuclei will be equivalent to the mass energy of the uranium-235 and the neutron. And in the thermal region, we can neglect the neutronic kinetic energy. So this will be the mass, and the mass equal this the excitation energy can be calculated using this difference into 931.502 MeV, and it is obtained as 6.5 MeV. So the excitation energy for uranium-236 is obtained as 6.5 MeV. But we know that we already had the calculated value for the activation energy, that is 6.2 MeV, which means that the compound nuclei require 6.2 MeV energy to overcome this Coulomb barrier, but 6.5 MeV is released by forming this compound nuclei, which means that there is readily available this 6.5 MeV, which is more than this 6.2 MeV. So by just forming this neutron with uranium-235 and forming this uranium-236, this fission is readily possible without any energy, without any extra energy. So that is the reason why this uranium-235 is fissionable by the thermal neutron, or neutron with zero energy. The similar calculation for the uranium-239 gives this kind of excitation energy, means this mass of the excited state of the compound nuclei uranium-239 minus mass of the ground state of uranium-239 into C square provides this value, that is 4.8 MeV. But we have the calculated activation energy value 6.6 MeV, which means we require 6.6 MeV for the uranium-239 for the fission, but already 4.8 MeV is released, means extra 1.8 MeV is required to occur the fission. So that is why at least we have to provide 1.6 MeV as the kinetic energy of the neutron. So that is the reason why the fission of uranium-238 is possible only using these fast neutrons, means neutrons of the order of energy in MeV. Okay. Now the question arises, why the difference in excitation energy? The uranium-236 and uranium-239 are the isobars very near, then why so much large energy difference, so much large excitation energy difference between uranium-236 and uranium-239? So the important factor, the most important factor behind this difference is the pairing term delta in semi-empirical mass formula. We know that pairing term will be positive for the even nucleus, means evenly paired case. This pairing term will be more positive, and which will be 0 for the even odd and odd even nuclei, and it's negative for the odd nuclei. For the case of uranium-236 and uranium-239, we know that the proton in both cases are 92 and is always paired, but the neutron in the case of the uranium-236, which is formed by absorbing the one neutron by the uranium-235. So when absorb the neutron number n becomes even. So the neutrons are gets paired. So as the pairing of neutron occur, the binding energy is increased by delta. So the binding energy of this uranium-236, this compound nucleus, increased by delta, the pairing energy, which is equivalent to 0.56 MeV roughly, which means that as the binding energy is increased, the mass is decreased. The mass energy is decreased. In other words, that much energy is extra released. So that much energy is available by forming this compound nuclei, extra available. And in the case of uranium-239, as it absorbs the neutron number becomes the neutron number is already an even number. It's already an even case. Uranium-238 is an even case. So this neutron number becomes odd by absorbing the neutron. Means from those negative level, due to the pairing energy term, it comes to decreased by the binding energy is decreased by delta amount. Compared to that even case, even the previous case in uranium-238, which was even, compared to the level of uranium-238, as it absorbs one neutron, it becomes odd even, and the binding energy is decreased by delta, which means that the binding energy decreases means the mass energy increases. That is, that much energy is lost during the excitation. So the net difference due to the pairing energy terms in excitation energies will be 2 delta, that is nearly 1.12 MeV. And this difference accounts the most part of the difference between the excitation energies of uranium-236 and uranium-239. It is here, in this case, it is actually 1.8 MeV, but up to a limit it accounts, so it can be accounted as a reason for the difference in excitation energy for uranium-236 and uranium-239. So this is the case. So for uranium-236, actually, in the absence of pairing, we can say that the level was this dashed line, and due to the pairing, this energy is decreased by delta, the pairing energy. And this difference between the ground state of uranium-236 and excited state of uranium-236 is the excitation energy, and this excitation energy gets increased by delta. And for the case of uranium-239, the ground state of uranium-238 in the absence of, or even uranium-239 in the absence of pairing, or in the absence of the pairing term, are expected at this level. And as now the pairing is removed, the energy is increased by delta. So the ground state is moved to this level, this upper level. And now this difference between this uranium-239 and uranium-238 is the excitation energy for this uranium-239. So comparing the change in excitation energy for the uranium-236 and 239, there is 2 delta difference, which were absent if the pairing energy term was absent. Okay. Now, how this energy is distributed among the fission products? We know that there are 2 major fission products. and there will be more neutrons and other radiation products. So we can take one example for the fission. That's again the uranium-235. One of the possibilities, this one, uranium-235 plus N provides this uranium-230 forms the uranium-236 compound nuclei and split into this rubidium-93 and cesium-141 with 2 neutrons. There are several possibilities. We already have discussed the mass distribution. Okay, so the Q value for this particular reaction is calculated as 181. So taking other possibilities also, other fission fragments also, roughly the Q value can be obtained. The same Q value is obtained almost nearly this 180, 190 Q value, 190, 200 Q value is obtained. So we assume approximately 200 MeV energy is released in fission of uranium-235. Please note that this Q value is the total energy released in a nuclear reaction. So we can assume that approximately or on an average 200 MeV energy is released in fission of uranium-235. So once the fragments get separated, get splitted, the Coulomb repulsion energy drives them apart and gives them kinetic energy, means converting the potential energy to the kinetic energy. Since the neutrons carries a very little amount of angular momentum, since the neutrons carries a little amount of the linear momentum, since it has very negligible mass compared to the larger fragments, so the two major fragments carry almost all momentum, and as per conservation of angular momentum, conservation of linear momentum, the both part means both fragments will have equal and opposite momentum. Since before the fission, the momentum was zero, nearly zero, neglecting the momentum of the neutron, the incident neutron. So after the fission also the momentum will be zero. So by that conservation of momentum, these major fission fragments will have equal and opposite momentum. That is, if the first fragment is M1 and the second one is M2, then that means M1 V1 equal to minus M2 V2. Okay. So by the magnitude, the momentum of the two fragments are same. So M1 V1 is equal to M2 V2. So that the ratio of their momentum, that is M1 V1 by M2 V2, and squaring each term and then taking this one by 2 on other side and rearranging it, we can find this this ratio of kinetic energy just like this one, half M1 V1 square divided by half M2 V2 square, the kinetic ratio of kinetic energies of the first and second fragment, which is equal to M2 by M1, means they are inversely proportional to the masses. Means the light fragment will have the higher kinetic energy and the heavy fragment will have the lower kinetic energy. Okay, so this is the distribution curve, the energy distribution curve. So this 61.4 MeV is the given value, but after the calibration, the correct value is 66 MeV, and here this maximum value is 98 MeV. So there are two peaks one about the 66 MeV and one about the 98 MeV energy. So we can establish that these results are consistent with these experimental results, means this mass energy distribution and this energy distribution. Sorry, this mass distribution and this energy distribution. So the ratio of masses from the mass distribution, the late M1 by M2, we take this M1 as the light fragment and M2 as the heavy fragment. And as an average, we can take these peak values, that is this M1, this light fragment is centered about 95 and the heavy fragment is centered about the 140. So this is M1 by M2 is 95 by 140, that is 0.678. At the same time, the ratio of kinetic energy, which we expect that this M1 by M2 will be equal to this Ke2 by Ke1. That is, the Ke2 means the kinetic energy of the heavy fragments, which will be the lower one. That means this lower kinetic energy 66 MeV, and the Ke1 is the kinetic energy of the light fragment, which will be the upper kinetic energy, that is 98 MeV. So 66 by 98 MeV, that is 0.673. So up to a very good accuracy. So these results are consistent with each other. So these observations are established. These relations are established. Now the distribution of energies appears to be a characteristic of the mass distribution. Just like the mass distribution, there are two bumps. And this suggests that nearly 165 MeV energy, means the 66 plus 98 is approximately 165. It is actually 164, but approximately we can take it as 165 MeV. That is nearly 80% of this 200 MeV. All are the approximations, and it's carried by this 80% of energy is carried by the major fragments, and it is as their kinetic energy. On an average, 5 MeV energy is carried by neutrons. And the rest energy, means this is almost 170, and the rest of the energy is shared by the formed gamma rays, means the gamma rays produced at the instant of fission itself, and they share nearly 8 MeV. And later, from the radioactive decays of the fragments occur, and where the 19 MeV is released from this beta decays, and 7 MeV is released by gamma decays from those radioactive fragments. So these are the ways the energies are released, but we can say that the useful energy will be the kinetic energy by the fragments, which can easily exploited to the outside. Okay, thank you.